Michael Warzecha earned his bachelor's of science degree in aerospace engineering at the University of Michigan and a master's of science in mechanical engineering at the University of Washington, and holds a professional mechanical engineering license with the state of California. He has over 30 years of experience working in aerospace and mechanical engineering. His current job is developing a hydrogen fuel cell powered semi-trucks in West Sacramento. He is an SBAS board director and is also a NASA solar system ambassador. So we've got a couple of them on the board now. Which is just great. So with that, I think we can just turn it over to Michael and hope his audio works.
Thank you. Thank you, Chuck. And let me go ahead and share my screen here. Give me a moment. Okay, can everybody see my screen?
Yeah, good.
Okay, let me just switch to full screen mode. Okay, before I begin my presentation about Dr. Edwin Hubble, I will just give a brief mention about Solar System Ambassadors. And this is a volunteer program with NASA JPL, and people from all walks of life work on this program. And our main goal is to reach out to the public regarding basically STEM, science, technology, engineering, and math things, talk about space exploration, what the current missions with NASA are. And for example, with the launch of Artemis, there were speakers and whatnot. Also, James Webb, we had lots of speakers covering that. We've got over 1,000 ambassadors in all 50 states and territories. So if anybody wants to have a speaker or help with a school program, nonprofit program, go ahead and contact us. And we do have a website. The website's down here, but simply just do a search on Solar System Ambassadors and it'll take you to the webpage. You can look up events, a directory of ambassadors, news, what's going on with NASA, etc. And since I'm on the board, you can reach me on the SVAS website. Go ahead and email me if you need help getting coordination or getting a speaker or whatnot. I'm doing presentations at the Community Observatory later this year. Those will be posted to the SVAS site. And I can also point to a different ambassador that could help you with a specific school project. So with that, I'll start my presentation. This is about Dr. Edwin Hubble. As his quote says below, the universe is unfolding as it should. We all know about the Hubble Space Telescope. And we know that starting at the end of the 20th century, the Hubble Space Telescope revolutionized astronomy. There's no question about that. And our understanding of the universe has dramatically improved with its discoveries and continuing discoveries. They're trying to make Hubble last, I think, past 2025. There's talk of having SpaceX boost the orbit of Hubble in the near future. So hopefully that'll come true. Now, we always hear the name Hubble, but I think a lot of people don't know the background and history of Dr. Edwin Hubble, the namesake of the telescope. And at the beginning of the 20th century, like his namesake, the Hubble Space Telescope, he rewrote astronomy. His discoveries completely upended our perception of the universe. And in this talk, I'll talk about basically his life, just give a brief biography of him. I'll talk about the efforts of mankind to understand our place and size of the universe, and then what Edwin Hubble did in his time to dramatically improve that knowledge. So first off, the early years. Dr. Edwin Hubble was born in 1889 in Missouri. And he loved science as a schoolboy, spending many hours reading science fiction. I can definitely relate to that. He had 7 siblings. He was a middle child among 7 siblings. His father was an insurance executive, so he had a good childhood growing up. And I can also relate to this very much. He was an excellent student in all subjects except spelling. And that's definitely somebody who I can relate with. He received his first telescope at age 8. So he had a very early attachment to astronomy. And we all know about him as being a great astrophysicist. However, he was also an athlete, and a very good athlete. He excelled at baseball, boxing, football, and track. And his college education is very interesting, actually. He earned a BS in mathematics and astronomy from the University of Chicago in 1910. And being the skilled athlete, he led the University of Chicago basketball team to their first Big Ten conference title in 1906. And when I first read this, being a Midwesterner, of course, as a Michigan grad, I said, wait a minute, University of Chicago is not in the Big Ten, but actually back then it was. It obviously no longer is part of the Big Ten. Now, interestingly enough, he went off to Oxford and became a Rhodes Scholar. And he actually finished law school in Oxford. So he began as an astronomer and then became a lawyer. And he wasn't too crazy about law school, even though he was actually very good at it. A large part of it was his father wanted him to become a lawyer. When he finished Oxford, he came back to the States and he taught Spanish and physics as a high school teacher. Now, returning to his first love, and this talks about his issue between law school and astronomy. He said, I chucked law for astronomy, and I knew that even if I were second-rate or third-rate, it was astronomy that mattered. And when his father passed away, he decided to go back and earn a PhD in astronomy. He went back to the University of Chicago. And in 1917, his dissertation was Photographic Investigations of Faint Nebula. And this will become a critical point when I begin discussing his work in the 1920s and 30s regarding the expansion of the universe. Now, we all know what happened in 1917. America entered World War I. And before I do that, let me mention him as a person too. When he was a PhD student, he was the head of the Snell Hall dormitory at the University of Chicago, and apparently there were rough elements there. But he had no issue being the disciplinarian at Snell Hall, because he said, quote, "They never gave me any trouble, partly because I had been a Chicago man and because I boxed." So I got a feeling back in the 1910s, they could do a lot more with discipline than they could now as far as keeping kids in order. But going back to 1917. In 1917, before he even finished his PhD, he had secured a position at Mount Wilson because of his academic reputation. And basically, he was all set to be a professional astronomer before he even graduated. However, World War I had erupted. And after finishing his dissertation, he telegraphed Mount Wilson and said, "I regret I cannot accept your invitation. I am off to war." And he joined the US Army. And he actually was commissioned as a captain in the 343rd Infantry and went to fight in France. And he was actually wounded in combat. He had been hit by a shell. He had a concussion and elbow injury. And so, but eventually when the armistice happened, he actually became a judge advocate for court martials with the US Army. So he stayed on with the Army even after the war ended, doing legal work. And finally, in 1919, he returned to civilian life with the rank of major. So he did pretty well for himself. He was the kind of guy that would do well in almost anything he approached. He immediately went to Mount Wilson. Before he left for the military, the director of Mount Wilson said, as soon as you're done, come back, please. And he wound up working at Mount Wilson for the rest of his career. And going a bit forward, I'll come back to his life at Mount Wilson. But when World War II erupted, he was in his mid-50s, and he actually wanted to volunteer and re-enlist and go fight again for the Allied cause. But the military said, "Well, thank you, doctor, but your scientific work is too critical." And what he wound up doing is he actually did research into ballistics. He did optical photographic research in ballistic explosions and whatnot, and it made a contribution to the war effort. And he actually won the Medal of Merit in 1946 for his effort. And again, he had the personality where whatever he took on, he excelled at. And going back a little bit, in 1924, he married Grace Burke, and that's her photograph right there. He also helped develop the Palomar telescope at 200 inches, which was the world's largest telescope for 40 or 50 years. He had a hand in getting that done. And him and his wife, they lived a very good life. They actually were very active in their community. They had parties, etc. And they were married until Edwin passed away in 1943 from a blood clot in his brain. And his wife lived on until 1980, and they had no children. I could not find much about Grace, but I do not think she remarried, and she did pass away actually not that long ago. At least to me, 1980 seems not that long ago. So right now I'll talk about his role, about the ever-expanding universe. And in the history of astronomy, the history of astronomy is an ever-growing universe as we perceive it, and an ever-shrinking human prominence. And this is a photograph of Earth taken by Voyager 1 in 1990 at about almost 4 billion miles away. And this kind of sums up how our perception of ourselves on Earth and the universe is always becoming smaller and smaller. And I'll talk about that. If we go back to ancient times, and this is actually a model of the universe that was developed by the ancient Israelites, where you picture the ancients picture the Earth as being the universe. That was it, and the sky above it, the firmament, was the other part of the universe. So the Earth was that big in our perception. The whole universe was Earth. And that lasted for thousands of years. And if you think about it, it kind of makes sense. If your perception is just your immediate area, you could see why you would think that. And if your fastest mode is walking or riding an animal, it would seem the Earth would never end. And then came the ancient Greeks. And in the 4th century, they figured out a few things. They figured out the Earth is round. And Eratosthenes in the 2nd century actually measured the size of the Earth to pretty good precision. And they looked up at the sky with the wandering stars that we now call planets, which is actually from the Greek language. They said, okay, the Earth is the center of the universe. It's not the whole universe, so now the Earth is beginning to shrink. However, everything revolves around it. The stars, planets, everything revolves around us. So we're the center of the universe, and we're still, a big part of it, but we're not the universe. And then came the 16th century. There was a Polish astronomer named Copernicus who further shrunk our perception of ourselves. And he said, wait a minute, the sun is the center of the universe. Earth is just a planet like all the other planets, and Earth goes around the sun with the other planets. So again, growing universe, shrinking Earth. Now we've been relegated to being just a planet around the sun. And at the time, everybody thought that the sun was the center of the whole universe, that the stars, again, were just another shell around the sun. So Copernicus had the right idea as far as the solar system model. It's just that 16th century astronomers hadn't quite realized, the proper place of our solar system in general cosmology. By the I got a header here. By the 18th century, with William Herschel and other astronomers, let me see here, 1 second. We began discovering that the sun is actually a star among many other stars inside of a group of stars. And they concluded that our portion of the Milky Way is the universe. So again, the universe keeps growing. They had the right idea, but did not quite understand that other galaxies existed, nor could they gauge the size of the Milky Way or where the solar system is with respect to it. So they were on the right track. And William Herschel certainly did see galaxies, but given his equipment at the time, he could not have been able to deduce what exactly a galaxy was at the time. And then we start entering the 19th century. And they used to call galaxies spiral nebula, because at the time they didn't think that the galaxies were outside of our own Milky Way. And this is actually the first photograph of a galaxy that was taken in 1888. And it's a 4-hour exposure with a 20-inch reflector and a 7-inch refracting guiding scope shot by Isaac Roberts. So the one question I've always wondered with imagers is, I don't think you need I'm a visual astronomer. I don't think you need a 4-hour exposure to get this equivalent with modern digital technology. But for 1888, this is remarkable that they could actually photograph a galaxy with this level of detail using glass plates and, telescopes. And the 19th century basically brought significant improvements in optical and mount technology. The Industrial Revolution really made a huge difference in our hobby. for the first time in history, you could photograph deep sky objects. And this marked the end of visual astronomy's multi-millennial reign of observation. And if you think about it, being able to photograph astronomical objects is a huge leap. You can do scientific work. And then we'll talk about what happened in the 20th century. By the time we hit the 20th century, there was a huge debate over the shape of the universe. Astronomers could see these spiral nebulas, and they weren't sure what they quite were. An existing theory at the time was that they are gaseous nebulas that are within the Milky Way, and that the whole universe is our galaxy. So depending on what measurements, 30,000 to 100,000 light years across is the universe. That's it. And now in the early 20th century, that seemed huge, but in hindsight, we of course know that that's tiny. However, there were people that began to think that maybe the spiral nebula are separate universes like ours and very far away. And there was a huge debate at the time between Curtis and Shapley talking about this. And interestingly enough, Curtis, who believed that the spiral nebulae were close by and weren't separate universes, won the debate. Shapley did not do as good of a job as Curtis, and that this was the going idea, was that the spiral nebula are not separate galaxies. The thing that made a big problem is the fact that we could not measure distances very accurately or very well beyond close stars. So we were just beginning to develop that. And that was our greatest obstacle in understanding the universe, is just being able to measure distances. Because if you think about it, you go outside in the night sky, you look up at the stars, you can't really tell if a star is far away or close by. You could have a bright star and you're thinking either it's really, really bright and far away, or it's very dim and close. You can't measure that without scientific instruments. And this is where Hubble comes in to change everything. So I'll go over just really briefly how they began to measure distances. The first one is called stellar parallax. And that is where you look at how a star moves in the sky based on the Earth's position with the sun. So it's kind of like when you look at an object and you look through your right eye and you see it, you look through your left eye and you see it moving slightly. That's parallax. And this was the first method developed to measure distances in astronomy. And basically, if you ever listen to science fiction, you hear the word parsec. And we've all heard it, like in Star Wars, the Millennium Falcon did the Kessel run in less than 12 parsecs. Well, parsec is actually a distance measurement, and it's 3.26 light years. In astronomy, you have a unit of measurement in the sky called an arc second. It's a very small measurement. The moon's diameter is, I'll do math here real quick, 1,800 arc seconds in width. And if you were to move the Earth the distance to the sun, a star at 1 parsec or 3.26 light years would displace 1 arc second. And this method worked fairly well for nearby stars in our neighborhood. But once you start getting past, maybe depending on your instruments, a few dozen or a few hundred light years, the change is so small that you really can't measure it. And so our ability to measure stars in the 19th century, or distances in our 19th century, was severely limited because that was the method that worked at the time. Then came the first breakthrough. And if you're a variable star observer, you know about cepheid variables. And these are incredibly special stars. Lots of stars are variable stars. And what happens is a variable star will change in brightness over time. And there are lots of things that cause the changes. I'm not going to go into those. But Betelgeuse was a famous one a few years ago where, Betelgeuse is a variable star, and then all of a sudden it dimmed really sharply a couple of winters ago. Cepheids are very predictable. They actually have a very predictable pattern. They will brighten and dim. And they also will have what's called every star has an absolute magnitude, meaning that at 10 parsecs from a star, you measure a star's luminosity. And that's kind of a yardstick to say, oh, this is a bright star because at 10 parsecs, it has this magnitude, or it's a dim star because it has this magnitude at 10 parsecs. And a famous female astronomer named Henrietta Swan Leavitt in 1908 discovered a very unique thing, that a cepheid will go through a series of brightnesses and dimnesses, and it has a very set period where it'll be bright and dim and bright and dim over several days. The longer the period, the brighter the star's absolute magnitude, and it is consistent. So if you had a star that, let's say, had a 50-day cycle, it had a set magnitude no matter where the star was or whatnot. You find a 50-day cycle cepheid variable, it has the same absolute brightness. And if you think about it, you've just found an incredible yardstick to measure star distances. If you have a star, let's say in on the opposites or in the Magellanic Cloud, tens of thousands of light years away, you measure its cycle time, you now have its absolute brightness. Then you look at it and say, okay, it's this bright, apparently bright in my eyes, and it has this absolute brightness. Based on the difference, you can calculate the distance very easily. And this was huge. And Hubble took advantage of that. And before I talk about cepheids further, there's a question that was also perplexing astronomers, and that was, did the universe have a beginning, or did it exist with no beginning? And in the 1920s, a lot of astronomers believed the universe had no beginning. They said, okay, the universe has always been and always will be. It's called the steady state theory. Even Albert Einstein believed that the universe had no beginning. There were some that theorized there was a beginning, but it was actually not a very prevailing theory at the time. And in 1927, independent of Hubble, and there's a common misconception that Hubble created the Big Bang Theory. He did not, and I'll get into that. In 1927, independent of Hubble, astrophysicist and Catholic priest Monsignor Georgius Lemaitre had a radical idea, that the universe began from a single point, a primeval atom, and expanded into the universe. And he essentially came up with the idea for the Big Bang. This was a very initial idea of it, but he was the first astrophysicist to actually scientifically come up with a theory of the Big Bang. And at the time, the theory was widely debated. Not, a lot of astronomers did not accept it. Steady state really held its ground back at the early 20th century. And so before I talk about Hubble, I'll just summarize what we've gone over. First off, spiral galaxies were known, but they did not know what they were. We suddenly developed the first yardstick of measuring long distances, which was the cepheid variables. Practical telescope gear and photography was invented. And the idea of the universe expanding, or excuse me, the universe having a beginning was proposed scientifically for the first time in history. And that created the perfect storm that Hubble stepped into and left his mark forever in science. So in 1923, while working at Mount Wilson, he photographed the Andromeda Galaxy, M31, and was the first scientist to actually resolve individual stars. And I think you can see where this is going. He also found a cepheid variable in the Andromeda Galaxy. So all of a sudden now we can say, we found a spiral nebula, we found a cepheid variable, how far away is it? And he originally calculated 900,000 light years. Of course, we now know it's over 2 million light years away, but he was on the right track. And he basically showed that, no, these spiral nebulae are not in our galaxy. They're not even close to our galaxy. They are mini universes very, very far away. That was radical. That was a huge breakthrough. And it also took the Earth and the solar system and further shrunk it and further made the universe bigger in our eyes. And with this single observation, he expanded our perceived universe like no other astronomer in history. And we're talking going back thousands and thousands of years to the first astronomers that looked up at the sky and figured out, that there were planets and stars. So this was just his first massive discovery in astrophysics. And for the next discovery that he did, I want to talk about spectroscopy. And I'll be brief about this. I won't go into a lot of details, but from our science and physics classes back in the day, we do know that if you take light, you can break it up into a spectrum, from ultraviolet to infrared and everything in between. And you can see the colors of the sky when you spread out a spectrum like that. You put the sun onto a prism, you get this. It's pretty cool. And this was actually originally discovered in the 17th century. So this idea goes way back. And one thing to bear in mind is in chemistry, when you have elements that are in this light source, they will actually create absorption lines. And this is just a crude graph here showing absorption lines. It could be hydrogen or helium or whatnot. So when you have a spectrograph and you look at it, you can actually figure out what the source's elements were. And they do this with stars. They take a spectrograph of a star, they can figure out what elements are present in the star based on absorption lines that pop up. And by the early 20th century, photography had advanced to the point where astronomical object could have its spectrum recorded. And the other thing I want to talk about is Doppler shift. So I'll introduce a couple characters here. We have Jenny, we have Billy, and we have Fluffy. I'm a cat owner, so I always have to have a cat in my presentations. And we'll have an ambulance going from Jenny to Billy. And hopefully Billy runs out of the way before the ambulance gets to him. But the ambulance has its siren on. And we've all experienced it where you have a Doppler shift, the car or the aircraft goes by and you hear the high-pitched sound of it approaching and then leaving. So, wow, car drives by. And the reason that happens is the sound waves are compressed by the motion of the ambulance in this case. So Billy, of course, will hear a higher pitched siren. Jenny will hear a lower pitched siren because the sound waves are extended and stretched. And Fluffy the cat will hear the classic sound of the siren approaching at a high pitch and leaving at a low pitch. So Fluffy will hear, wow, as the ambulance drives by. That's called Doppler shift. Light does the exact same thing. If you have an object that's approaching you at high speed, and I'm talking, tens of thousands of kilometers per hour, or per second rather, it's going to compress the light waves ahead of it, and it's going to cause the light waves to be bluer, to be shifted towards the blue end of the spectrum. So if Billy was a few million light years away from M51 here, the galaxy, and if the galaxy is approaching him, he would see the galaxy look a bit bluer or blue shifted because the light waves are compressed, just like the ambulance siren sound is compressed as it approaches Billy. Jenny here would see the opposite. Because the galaxy is receding from her, she would see the light waves stretched out and redshifted, or basically look more red. And just like the siren moving away from her, the sound waves get stretched out and the pitch lowers. Same thing with light, it becomes redshifted. Fluffy, who's perpendicular to the motion, his life is too short to notice a spectrum change. But because he's perpendicular to the galaxy would look normal to him. There wouldn't be a redshift or a blue shift. It would look just like a regular galaxy, as if it was not moving based on his time scale. Now, so what Hubble did is he began taking spectrographs of galaxies. And this is actually a typical spectrograph that he did. He didn't photograph it directly. What he would do is put a camera with a special device that would create the spectrum and then take the image. And to show how this would work is imagine that this is the spectrograph of the galaxy. And there's a couple of absorption lines right there from, I think it's calcium, and I can't remember what the other element is, but it was a common absorption line in stars. And with no relative motion, you can say, there's my spectrograph. Everything looks good. Everything's where it's supposed to be. What he discovered was that when he shot a spectrograph of the galaxy, the whole spectrum was shifted towards the red, just as in the examples of my cat and the two kids. everything, the whole spectrum line, the absorption line, the whole spectrograph, the absorption lines all shifted into the red. And the further away he looked, the more it redshifted. And for the very far away galaxies, he didn't achieve this, but we see this now, is the galaxies that are very, very far away, the redshift is so great that it actually goes into the infrared part of the spectrum, and we can't even see the redshift with human vision. So this brought up the question, going back to steady state or primeval atom. If the universe was steady state, and Fluffy is back here on Earth looking at all of the various galaxies around him, through telescopes, of course, he's a very smart cat. If the universe is steady state, we would expect the galaxies to be moving kind of like pinballs, bouncing around, some galaxies colliding, some moving away from each other. And we should kind of have like randomness. Some galaxies would be redshifted because they're moving away. Some galaxies would be blue shifted because they're coming towards us. Some wouldn't be shifted at all because they're perpendicular to us, etc. Now, if the universe is shrinking and we looked up at it, we would expect all the galaxies to be blue shifted. So Fluffy here is looking at the galaxies and they're all shifted towards the blue side of the spectrum. And he would say, hey, the galaxies are all moving towards me. And if the universe is expanding, we would of course expect all of them to be redshifted away from us. And that's exactly what he discovered. When Hubble took his spectrographs, he saw that almost every single galaxy he imaged had a redshift. I mean, consistently. There were very few that were blue shifted. Andromeda actually is a little blue shifted because it is approaching us, but that's a local phenomenon. But everywhere he looked, redshift, 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 redshift. And this showed that the universe was expanding. And it was, again, this was the next groundbreaking thing that he discovered. He said, not only are these galaxies really far away, but almost all of them are racing away from us. And his spectrum data confirmed that Monsignor Lemaitre was correct. Of course, I'm compressing timescales a bit. It takes years for this type of research to actually fall into theories and whatnot. So it wasn't exactly like in 1929. Oh, everybody had the Big Bang Theory down pat. It took a while for all this to happen, but basically his data, Lemaitre's research, all said our universe is expanding and began as a single point. And this is how the Big Bang Theory was born. And it gave a perception of the universe that's even vaster than before. So within a very short time in the early 20th century, we went from the Milky Way being the whole universe to a gargantuan universe where there's millions to billions of galaxies and are all rushing away from us because the universe is expanding. And the universe had a starting point. And even Albert Einstein admitted that he was wrong about steady state. And, being a scientist, you discover that you had a wrong idea, and then, well, so the data says chuck the idea, and he did. He said, okay, I was wrong. Pardon my German. So going back to Hubble, and this is the only time I'll show an equation in my presentation. What Hubble discovered is something really neat, and it's called the Hubble-Lemaitre law. This is a recent change because anybody that studied astronomy in the past heard this as Hubble's law. Recently, they actually credited both of them, Hubble and Lemaitre, in coming up with this. And it's very simple. What he discovered is a galaxy's distance is proportional to its relative velocity. And the relative velocity is gained from the redshift. So basically, if you measure the speed of a galaxy running away from you based on its redshift, you can figure out its distance. It's a linear relationship, which frankly, after studying science, is amazing. And now we have a yardstick where we can measure distances on the order of billions of light years and get a really good grasp about how big our universe is. And all of this happened in the last 100 years. And that's what really amazes me about this is, we had 5,000 to 6,000 years of astronomy. And then it's not until the last century that we really got a grasp as to how the universe is built. That just blows my mind, to be honest. And the fact that we have the simple Hubble-Lemaitre equation to explain it, a nice, easy linear equation. And here's actually his data where he did figure that out. Now, one thing in the 1920s, he didn't have it exactly figured out. Some of his distance measurements were off a bit, but of course, he set up the principle, and then they refined these rules as they got better at them. So we thank him for the initial research, and then of course the refinement that happened to where we are today. But there's more. Hubble was an excellent soldier. He was an excellent lawyer. He was an excellent athlete, and he didn't stop there. Because at the time we did not understand galaxies, he continued his research into figuring out how galaxies formed, how they're shaped, and he created the Hubble classification scheme of galaxies. And that's where we have, in this case, we have elliptical galaxies, we have spirals, we have barred spirals, and he began developing that too. And that, of course, has been refined over the years, but this was his idea. And thanks to him, we finally understood the spiral nebula, that in fact they are mini universes, just like our Milky Way, and a heck of a long distance away. And what he did is he basically made Earth's place in the universe extremely tiny. If you think about it, there's trillions of stars out there. Our sun is just one of many. And Earth went from the perception of the ancient Hebrews, where the entire universe was the Earth, to this very small, fragile place in the universe. And in my opinion, very precious for that. I think the fact that we're so small in the significance of everything makes our existence extremely precious and important. And I'll just talk a little bit more about continued cosmology after Edwin Hubble. The battle between steady state and a creation of the universe did not end, because in the Big Bang theory, you have the momentum from the Big Bang that's expanding the universe, and then you have gravity trying to bring it all back together. And back in the day, back in the 70s and 80s, the thought was you had a Big Bang, of course, the universe kept expanding, and then eventually would kind of reach an equilibrium where the momentum would slow down and then gravity would catch up to it. So all of a sudden, gravity begins contracting the universe. And then you have what was called the big crunch, where the universe would come back into a single point and then cycle back and create another Big Bang. And in a way, it's kind of a new form of a steady state universe. Was called the Oscillatory Universe. And that was actually a popular theory. I remember watching Carl Sagan's Cosmos in middle school back in 1980, and this is one of the things he actually talked about was, could the universe be oscillatory? And from what they understood at the time, it actually kind of made sense. But as mentioned, Edwin Hubble certainly made lots of breakthroughs in understanding of the universe, and his namesake, the Hubble Space Telescope, did that too. And the Hubble Space Telescope even kept pushing the universe's size further out than we imagined 100 years ago with Dr. Edwin Hubble. What this Hubble telescope showed is we vastly underestimated how many galaxies are in the universe. There were efforts called the deep field image, where they would basically point Hubble at a blank spot in the sky. And the angular size, I don't have it handy, but it would be as if you took a soda straw and looked up at the sky. That's how small of a patch you would image. And they would spend days and days and days imaging this really tiny spot. The scientists that did this said, we're not going to see anything. Well, I'm sure we've all seen this. When they processed the images, that little area of a soda straw showed, for better words, an infestation of galaxies. The amount of galaxies we can spot in those deep fields is staggering. And if you look at this image, you can see those little tiny dots. Those are not stars. There's only a few local stars in this photograph. all those dots are galaxies. All those dots are a mini universe. All those dots are basically have billions of stars. We know that almost every star has an exoplanet. So there's probably trillions and trillions of exoplanets in this photograph. And that is just staggering to think about. So the Hubble Space Telescope, like its namesake, further expanded our perception of the universe and further shrunk us as the Earth into just a very, very, minuscule part of all of it. And if you have a chance, all the Hubble photographs are public domain from NASA. Pull up the raw file on this image and just explore it. I've done that, and you can just see galaxy after galaxy after galaxy in this one image. And there's been more deep fields. I know that James Webb will be doing deep fields as well. I don't know the status on that yet. And the last point I want to make is the ultimate vastness or heat death. With the Big Crunch theory, if you follow cosmology, the Big Crunch is not going to happen. And basically, what they're figuring out is that the expansion of the universe is actually accelerating. That has a lot to do with dark matter, dark energy, etc. And that's some PhD level astrophysicist stuff. So I can't go further than just explaining what they discovered. But in the end, gravity does lose the battle. And the going theory in cosmology now is that the universe will continue to expand forever. And that's the ultimate vastness, where the universe will not crunch over trillions, and I'm talking trillions of years. It will forever expand to the point where stars are burned out. Energy and matter are basically just scattered to the point where the universe will just consist of a really cold near vacuum state. And occasionally you'll get an interruption of a little stray subatomic particle going by. But, and they also theorize that space-time itself will begin to start ripping apart because the expansion will just be so vast. So this is like the largest possibility of a universe expanding, further showing that, we are such a tiny part, and the vastness is just unimaginable of what our universe actually is. And basically, my little headstone has the entropy equation, Hubble's law, and basically heat transfer, showing that heat death is right now the going theory of what will end up being our universe. That's all I had. So if anybody has questions.